So we had time series xt, transfer function 1 minus 0.82b divided by 1 minus 0.16b times 80. 80 is the random component. Standard assumptions apply normal, zero, mean, and variance required A. If you pick any value. We started with R1, I showed you how to do in R. We rewrote it as MA infinity using long division. This time we're going to rewrite 80 in terms of AR infinity. I have a question in mind, but we'll save that for later. Yes, I just flipped it. So the process is exactly the same. What we would do is do long division again for this part right here, because you can go back and forth. And just like last time, I'm writing it in increasing or decreasing powers of b, and I'm going to replace that b by x so that you can relate it to algebra. So we can put it as x for now, change it back to b, and it's how it goes. So long division, we always include this term, and then we subtract. We've got to multiply negative 0.82x by something to get a value, so false. What?
Shouldn't it just be the inverse of what we used last time? To get the 0.16 into the negative.
So, okay, I see what you're saying. This is 1 over
5.125.
5.125, which would be 0.19.
Was that 5?
Okay. Approximately. And then we would have 0.195. Subtract the 2, that will go away, and you will have 0.9805. Then we could write it using the standard long division way, which is good. What did I put there? 0.05. Oh, that's not 0.195. 0.805.
Okay.
Good. What did we do here?
The last time was the next step, or what did we just do?
Yeah, the next step.
rewrote it as a series.
We rewrote it as a series, so we have 0.195 plus 0.805 times 1 minus 0.82x inverse, which is a geometric series, sum, infinite sum, so I will have 1 plus 0.82 squared. Oops, my brain's going ahead of me. 0.82 plus 0.82 squared. Dot, dot, dot. We don't want to do all that, so we can simply write it as a sum. 0.195 plus 0.805 sum I equals 0 to infinity 0.82 raised by.
Getting the backwards operator.
The X rolling.
Done. And B raised. Okay, I changed the X flat to B. Last time we split the first term, so 0.195 plus 0.805. When I is equal to 0, I'll simply end up having 1 plus the remaining part of the series, 0.825 b raised by. And we are multiplying by xt over here. So let's not forget the xt part. So on the left hand side, we have this term times xt. Right hand side is equal to 80. I'll write it over here. So this is the part we solved. It's right there, 0.195 plus 0.805. 1 plus sum I equals 1 to infinity 0.82 raised I b raised I. Entire thing multiplied by xt. And that would equal to 80. Good. Well, xt still remains outside. 0.195. Let's distribute that 0.805 inside, so 0.805 plus 0.805. Sum I equals 1 to infinity 0.82 raised by bi, or b raised I. And that would equal to 80. Good. If I expand this, I'll end up having xt 0.195 plus 0.805 is 1 plus 0.805 times less than 0.82 times b. Second term, 0.805, 0.82 squared times b squared. Expanding the series out, plus 0.805 times 0.82 raised through. We get something like that. keeps on going, and that would equal to a sub t. Well, you can tell me how to calculate it. The first one's easy, that is approximately 0.6. No, 6.2. You have the calculator.
0.66.
6.6. Oh. The next one is approximately 0.65, multiplied by 0.8, 0.48 something. 0.4.
0.54.
0.54. 0.8 times 0.82 cubed.
444.
0.444, we'll leave it as 0.44 b cubed plus dot 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 equals a sub t. If I distribute xt, I'll have xt plus 0.66 xt b plus 0.54 xt or b squared xt 0.44 b cubed xt plus dot 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 is 18. I want to get rid of the backwards operator. What should I do? Simply apply it, I'd end up having xt plus 0.66 xt minus 1 plus 0.54 xt minus 2 plus 0.44 xt minus 3 plus dot 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 equals 8. Today,
Well, how would the xt times be? Just because of the xt.
this one, xt minus 1. Backwards operator. Good. Now, do we see all the phi weight or psi weight? Yes. If you rewrite it as a sum, which probably was here, I can simply write it as sum k equals 0 to infinity. The positive part we use psi, correct? Doesn't matter. Psi k and xt minus k equals 80. So, that is a concise version of writing it, where psi 0 is 1, psi 1, 0.66, psi 2, 0.54, psi 3, 0.44, and so on. What is happening to the coefficients? It's going down. Do you believe the series is absolutely solvable? Yes. So is it going to be stationary?
Yes.
Yes. Okay. Question. Earlier. Did I have to do long division? And wrote it this way, but my question is it necessary that we do long division? Error.
I don't think so. You can just divide the coefficients for b, and then depending on which way you're doing it, you can do the reciprocal if you're going the other way, and then you subtract it from
divide the coefficients of B. What do you mean?
The 0.16 and the 0.82.
No way, it's bad algebra.
Well, it would be the same when we're doing the long division, you get the same, and then you subtract it from one. And then you do the.
Oh, I see what you're saying, okay,
So
but
you're doing the same thing, but just without.
without even
Yes.
thinking about the division
Yeah.
part, is there a different way of doing it? Without even thinking about division. Hence, we have applied it a couple of times already.
I don't know if this is what you're looking for, but, can you multiply the whole thing by whatever's on the denominator and solve it quadratic?
I'll give you a hint. Maybe you will see it then. 1 minus 0.16b times 1 over 1 minus 0.82b xb equals 18. Running out of space. Breaking my heart here. We just did it. We had something over 1 minus 0.82b and we
Oh, that's a geometric series.
it's just a series, right? I could have started right here, put it as a series and gone from there. Yes? But why did we do long division? This case, it is easy. But say for instance you had an AR or ARMA 2 model, then you won't have a polynomial that is of degree 1. You would have a quadratic denominator. If you had an AR33, you would have a cubic prime. So in those cases, the only thing that you can do is long division. Good. Most processes don't need a whole lot of parameters. Given the AR infinity part and ARMA 1 that we started with, which should we use? You have a series and one, you can either use ARMA 1 or you can use AR infinity. Which one should you use?
The ARMA,
Why?
I forget what you call it exactly, but because it depends on less steps.
It's not steps, parameters, coefficients, weights. Principle of parsimony. We always want a parsimonious model in the sense fewer the coefficients, the better. If you can't explain something with 4 coefficients, and if you can't explain the same series with 100 coefficients, which is the smart thing to do? 4, right? So we need to go for a parsimonious model. So I'm just showing this over here because we can use this to come up with covariances and things like that. Good? Are we clear? Okay. My mind always goes to process because it's stochastic processes, but I'm referring to a series. I showed you what a non-stationary series is at the very last lecture or so, yes. Non-stationarity typically happens when you have a unit root. Unit roots result in non-stationarity, and we want roots to lie outside the unit circle. for it to be a stationary basis. But just because you have unit roots and series is non-stationary doesn't mean you have to pack it up and leave. There are characteristics such as Onstein Uhlenbeck finance. It's a process that pops up quite often in stock market. It's a non-stationary series, but is it possible to model them? Yes. What do we do? The model is called a Riemann. The I part is integrated. By all means, it's more like a summation. So a Riemann, the I stands for integrated. What is our standard equation for an Armand model? You can look in your notes. The goal is to define a non-stationary series. Do keep in mind, this is not the only way. There are plenty of other models. All the names they come up with to this day, it fascinates me. It's got Arch, Gosh, Dar, Dharma. It's not like Dharma as in religion Dharma, but Dar, Dharma, Arch, Gosh, integrated Gosh, keeps on going. I don't know if I can get to Arch and Gosh, but there are a whole lot of models. For starters, let's stick with a Riemann. This is the model that one would fit if we have non-stationary. So, okay. What is the notation for this? That. I'm trying to stick with the book's notation, so. We've got phi, we've got sine, we've got theta. This is cosine with cosine. Another Greek letter, now you know. Sometimes I've got to go back and look at, well, how do we pronounce this? There is cosine, there is cosine, eta, beta, gamma, alpha, it just keeps on going. Do we see the difference? We just have to make the connection between the two. If you take phi of phi and multiply it by 1 minus b raised d, then that would equal to phi, or whatever that is. Do put a note in the text that might call this WT. Should we just use WT? It doesn't matter, right? I like to keep it as things. Okay, so we have, but I put a note, and the book calls this W sub T, I believe. It's been a while since I've been having. Phi of B times 1 minus B raised D. Long time ago, we did learn about 1 minus B. It was in the homework also. I'll give you a hint. It's got something to do with the trial. Joe.
Oh, I'm sorry, Andreas.
Are you stretching? Okay, Andres.
With the difference
backward.
Okay, what difference?
Forward, backward.
Backward difference operator. Okay, simply the backward difference operator. We used upside down triangle, fancy word. Now look. Good. 1 minus b is the backward difference operator. That will give us that expression. Why do we call it backward difference? Side note, this is just to refresh your memory. If I did xt times 1 minus b, I'd end up getting xt minus b times xt, which is xt minus 1. Do we agree? Backward difference. Xt minus the previous one. Okay. That d is the order of the integrated part. Oftentimes, d doesn't exceed, say, 4. I'll be surprised if it went past 3. So common values 0, 1, 2. Usually, d could be 0, 1, 2. Here's a question. If d is equal to 0, our expression is going to reduce to something simple. What is it? This would simply be the R normal. Why? Well, if d is 0, it is an operator, but we are going to treat it as a variable. Upside down triangle, number rate 0, 1. So I simply go back to phi of phi, which will take me back to an normal. So this is simply on the tree. Good. When we write it over here, put model star because all I'm doing is giving it a name. On PQ is the same. P0 Q. Good. But that wait.
Would that be a rima there?
Unlikely. So since I have armor PQ and I have armor P0Q, I'm adding a new value, a new parameter in there. That corresponds to the integrated part. So P order of ARQ order of MA 0 would simply be the degree or order of differencing. So in this case, it is the Riemann P0Q. Good. Other cases, if I have a Riemann P1Q, P2Q, is it possible to come up with an armor representation? Absolutely, we can. Let's see when we get to example 4, I believe. We would simply write it as a Riemann P, D, Q. It's like that chicken restaurant. So last time I used a Riemann when I simulated, because a Riemann is the general specification. if G becomes 0, Riemann becomes R. That's all. Are we clear? We can write things in an interchangeable manner. For example, just like we did here, I can divide by 1 minus b raised d and express it as a sum on this side, as a sum on that side. It's the same process. Let's move further into doing this chapter 1 stuff over and over. But are we clear about transfer functions, about phi of b, theta of b, the c of b, Armin, Riemann, AR, and A? Okay, good introduction. Chapter 2 deals with some theoretical stuff, some of which I kind of started already. Expectation, yes. Do we remember? I expect you to know about expectation. But moving on. Anytime you see E, I said you can replace it by. So when you see expectation of X, an easier way or easier thing to relate this to will be mu. Very good, it is mu, but what is mu? Mean, theoretical mean, it is the parameter probably that you do not know, but if you want to easily remember what that is, take that E, replace the entire thing by a sideways M. I equals 1 to n, 1 over n, and put xi. So E simply moves or becomes that easier way to remember. We have used the word stationary time and time and time again. But what is stationarity? Well, I've given you the definition, or I've given you an example of stationarity. And on the stationary series we saw in the simulation. But how do we know something is stationary or not, theoretically speaking? There are conditions. They have xt minus 1, xt minus 2. Those are all the time variables. All of them are random. Reason being, each observation that you make has a t in it. So a random component is always there. And if you have xt dependent on xt minus 1, xt minus 2, the way we write it is xt dash xt minus 1, xt minus 2, This simply means xt depends on all of those. People who took 3162, what does that remind you of? So probability of XT is going to depend on all previous values, right? That is simply a conditional probability. What is an extension of conditional probability? We started with probability. What is the next step? Start with the letter D. Conditional distribution. What is the difference between, probability and distribution? So it is a function, correct? Which would mean I have a whole range of values. I'm not looking at a single value. Probability, we're finding for one event, one outcome. Here, I'm going to look for all possible outcomes. So the condition is this. You don't know probability theory, that's fine. You can learn now. We're not going to derive stuff here. So that is a conditional probability, or XT depends on XT minus 1, XT minus 2, etc. Not a conditional probability. But if I write it this way, same event, but I'm saying that this is a conditional distribution. Okay? Because I'm going to define for all values of x. For a series to be stationary. Let's start with this. XT minus 1, XT minus 2, XT minus 3. This is not a conditional distribution, which is why I wrote that. There is a difference between the two. Here we are saying, well, the distribution of xt depends on all the previous values. Here, it is just a distribution of all of them put together. What's the name? Very good, joint distribution. They are not the same. So it is a joint distribution of xt minus 1, xt minus 2, ... keeps on going. That said, so this is the statement that matters a lot. The joint distribution xt minus 1, xt minus 2, xt minus 3, ... keep on going, is the same as xt minus 1 plus k, xt minus 2 plus k, xt minus 3 plus k, ... Instead of k, one can use h. Did we use h? I think so. We'll stick with h this way, connect the dots. H, h, h. What is h? So, for any value of h, for h, which is a whole number, for any h, four numbers. The joint distribution of this and the joint distribution of that must be the same, no matter what H you pick. Do you think that that is an easy task to do? Those who did probability and statistics know the pain that's involved in finding a joint distribution for two random variables. Here, infinitely many, even if you say I have an AR5 model, you have 5 variables. Joint distribution of 5 variables, painful. So what we are saying is not only it should satisfy for the 5 variables that you start with, it has to be the same in distribution to any set of variables if I change the lab. Not an easy task. It is not something that one would want to verify if they want to. No actuary in their sound mind would do it, but then an actuary doesn't have a sound mind. Until they're in the distance. This. And then range is is what we call a strict sense stationarity condition. Stationarity in the strictest sense possible. This is not something that we would be able to do in all cases. Even I wouldn't know it because the derivations get tricky. So what we rather do is go for something simpler. We rather go for weak sense or wide sense stationarity. Mathematicians or statisticians, they go for weak sense. Wide sense is something that's used in electrical engineering, significantly. They mean the same. I say to Marshall, you say to myself, we'll talk about the same thing. So what is the condition? 1. Expectation of xt is mu, i.e. it is a constant for all t. Remember, I mentioned this very first or second day of classes. I have a constant mean, I can subtract that. If I don't have a constant mean, I have a process that's going all over the place. Obviously, this is an easy condition to verify. That is hard, but something that will do the job, and this does, is this. Down the page. H could be either positive, negative, doesn't matter. Starts with the letter C. Covariance, specifically what kind? We all like to drive it. Driving covariance. Autocovariance. So autocovariance, xt, xt equals h. If h is positive, that's fine. Negative, that's fine. So if we have gamma h, this depends only on h. It depends on the lab, it does not depend on time. Good? That should also make sense, correct? If two things are correlated for any h, let's start with h equals -1. So I have xt correlated with xt minus 1. And I want it to be independent of time and dependent only on the life. And then I move on to xt minus 1 and xt minus 2. I want it to be independent of time, dependent only on the life. And I keep on moving every single step. They are related, but they are independent of time. In other words, they don't vary with time. If there is a variance, but it doesn't vary with time, then it is stationary. Correct? That's what stationary means. So, if these two conditions are satisfied, then we call it a stationary process. Going back to that original picture that I started with a while ago, I had an initial level and I showed you things go back and forth about that level. So there you've got variability, but they don't vary with time. There is variance, but things don't go like that random walk simulation. Are we clear?
If, does gamma need to be a certain value to be stationary?
No, it just has to be independent of time.